This work was done with Davis Foote, Anka Dragan, Stuart Russell, Eric Jenner, and Scott Emmons. So what about RLHF? RLHF is a method to steer reinforcement learning systems by trajectory comparisons. So humans basically compare two trajectories and then decide what is better, and that trains the system. And nowadays it's used a lot, for example, in ChatGPT, Gemini, and Claude. All of these use some variation of RLHF. But there are remaining safety problems. So some of them are, for example, that these systems can be jailbroken, or that they can show political biases or align with the political biases of the users. But we are looking at a different problem, namely the problem of partial observability in LLMs or later agentic systems. Like imagine, for example, you ask ChatGPT to Google something, then ChatGPT may search for it in the internet, and at some point it clicks on something, but you don't know what it did not click on. And so you as the user have partial observability. And based on this limited data, you give them feedback. So what types of problems might we see under partial observability? One of them is illustrated in the so-called smart vault by Paul Cristiano. So imagine you have a future AI system that is supposed to keep track of this diamond and make sure that it is not stolen. And you look at simulations of the behavior in order to train the system to be able to keep the diamond in its place. Then obviously, if on the camera image you see the diamond being there, you give thumbs up. Otherwise, you give thumbs down. But there is a problem. If you just see the camera image, then you might actually have the situation that on camera the diamond is there, but in reality some thief stole the diamond and just put a picture of the diamond in front of the camera. So this is obviously bad, but you didn't see this because of your partial observability. So we are modeling this type of situation. We're doing this by working with a Markov decision process framework with actions, states, transitions, and a reward function. We assume the agent observes everything. So in that sense, it's really fully observable. But the human evaluator only observes partially. And then we need to somehow model how the human makes the choices between two state sequences S and S prime. And our assumption is that the human basically observes O of S and O of S prime, and then imagines what state sequence could have generated that observation sequence, and then computes the expected value and uses the comparison of those expected values for the final choice. And in this framework, we observe several alignment concerns. One of them we call deceptive inflation, and it's when the behavior appears to be better than it is. So this is what we saw before with the smart vault. Another alignment concern is over-justification, where the model convinces you successfully of good behavior, but there is a cost to it. So you can, for example, imagine you have a child, and the child's task is to vacuum clean all the rooms, and it's evaluated by their parents. But now the child has an incentive to vacuum clean in exactly the rooms where the parents currently are, and this leads to noise disturbance. So the child did the right thing, but the act of convincing the parents that it did the right thing is in itself costly. And this is something we should expect in partial observability. So our result is that we prove that either deceptive inflation or over-justification emerge from RLHF under partial observations. And we also confirm these predictions empirically. So we show that when we vary some hyperparameters, deceptive inflation on the left and over-justification on the right basically emerge in those situations where we expect them. And then we think about, can we do better? And our idea is that maybe we can do deep RLHF under uncertainty by encoding the fact that the human is partially observable into the loss function. But for this, one would need the human belief model B. So the human's beliefs when seeing something, what do they believe happened in the state of the world? And conceptually, this works, and we show that in some toy problems, this actually leads to some improvement. But this cannot be immediately used because we do not have the human's belief matrix. So for future work, we think it would be desirable to look into the improvement of theory and practice of this modeling. We think it might be interesting to look at the right trade-off between expensive full observations and cheap partial observations.